Good morning students, I am Aher from RBNB College Rampur. Today we start the chapter Superposition of the waves. In this chapter we see the vibration in the string. We know the stationary wave. The stationary wave, it is the two identical progressive wave traveling along same path but in the opposite direction interfere with each other, forming a stationary wave. Now in this stationary wave, it is localized wave, it is standing wave. When it is produced on the string or a liquid column, there is node and antinodes are formed. The points at which the displacement amplitude is maximum, it is called as antinode, and the point at which the displacement is minimum, it is called as node. Now here we see the vibration in the string. Now consider here a string, it is fixed between two support. Then the string is plucked at the center, one loop is formed. Now here we consider the string, the transverse wave generated on the string. Now suppose this is the crest of the transverse wave traveling along the string. It is reaches at this fixed support and it is it is reflected back. Crest is reflected as trough and it is reflected from denser medium. There is phase difference of pi. Then this is reflected like this and forming a loop. Now at the support node is formed and at the center antinode is formed. Total length of this string, it is L. Now this is the first mode of vibration of the string. Now in next mode the two loops are formed. Now in this case the two loops are formed and again this is the stationary wave incident here and there is phase difference of pi. Then again this is trough, it is reflected back in the opposite direction forming a stationary wave. This is the stationary wave. This is the second mode of the vibration of the string. Now in third mode, three loops are formed. These are the three loops are formed and this is reflected back forming a stationary wave. Now we see the details of this stationary wave. Now see in figure A. In figure A, now in this case, the string is stretched between two rigid support when this transverse wave incident at this denser medium, it is reflected back forming a stationary wave, forming one loop. Now here, suppose L is the length of the loop, length of this string, then we can say that in this is the lowest mode of vibration. Two nodes are formed and one antinode is formed at the center. Then we can say that vibrating length of the string is equal to vibrating length of the string is equal to. Now here node is formed at this end and here again node is formed at this end. Therefore we can see that is vibration of the string is equal to length of vibrating string is equal to distance between successive nodes. Now suppose L is the length of string and the distance between successive node, that is the distance between two nodes, it is lambda by 4, where lambda is the wavelength. Then lambda is equal to 4L. Here lambda is the wavelength of this wave and L is the length of the string. Now we know the velocity of transverse wave. Velocity of transverse wave. It is given by V is equal to under root T upon M, where V is the velocity of transverse wave, T is the tension applied, M is the mass per unit length. Now we have the formula, the simple relation V is equal to N lambda, where V is the velocity, N is the frequency, lambda is the wavelength. Now we rearrange this formula for N. It is N is equal to V upon lambda. N is equal to V upon lambda. N is the frequency of that mode, V is the velocity, lambda is the wavelength. Substitute the value, we get N is equal to V, value of V, it is root T by M. 1 upon lambda into root T by M. This is the frequency, and substitute lambda is equal to, substitute this is the lambda by 2. Therefore distance between two successive node, it is lambda by 2. Here vibrating length of the string is lambda by 2. L is equal to lambda by 2. Lambda is equal to 2L. Substitute the value in this case. Velocity of transverse wave V is equal to under root T upon M. N is equal to V upon lambda. V is equal to N lambda. N is equal to 1 upon lambda under root T upon M. Thus N is equal to 1 upon 2L under root T upon M. This is the lowest frequency. This is the lowest frequency called as fundamental frequency. It is the fundamental frequency. This is the fundamental frequency. It is also called as first harmonic, frequency of first harmonic. This is equation number 1. Now we consider the next mode. In figure B, N1 is the frequency, lambda 1 is the wavelength of that mode. Now here in figure B, see, this is the transverse wave, this is incident on this denser medium, it is reflected back in the opposite direction, forming a loop. It is the stationary wave, it is localized wave, it is standing wave. Now here at the end node is formed. At the center, that is here, antinode is formed. Node, the point at which the displacement is minimum, the antinode, the point at which the displacement is maximum. These points are, there are in this mode 3 nodes and 2 antinodes are formed. Therefore, in this second mode, the 3 nodes and 2 antinodes are formed. Now, the length of vibrating length on the string, the vibrating length of the string is equal to, now in this case 2 loops are formed. Therefore, the length of this loop is L by 2, length of this loop is L by 2. Then we can say that the distance between this node is lambda by 2, distance between this node is lambda by 2, then we can say that is lambda 1 by 2 plus lambda 1 by 2. We get here lambda 1, L is equal to, that is vibrating length of the string is equal to L is equal to lambda 1. Again we know the relation V is equal to lambda, that is V is equal to N1 lambda 1. We can substitute lambda 1 is equal to V upon, we can substitute N1 is equal to V upon lambda 1. Then substitute the value of lambda 1 here, that is it is 1 upon L. Substitute the value of V, it is T upon M, under root T upon M, where T is the tension applied, M is the mass per unit length. Now suppose we multiply here 2 by 2, then the value of this, that is 1 upon twice L under root T upon M, it is nothing but N. Then it is twice N. That is, we can say that in this mode the frequency of vibration, it is N1 and it is twice N. Thus we can say that it is the frequency of second harmonic. This is the frequency of second harmonic. Then it is also called as frequency of first Aher tone. First Aher tone. Now in case of third figure or third vibration in figure C. In figure C, see the figure. In figure C, 3 loops are formed. Now this is, node is formed at the end, again node is formed here, node is formed here. There is antinode, antinode, antinode. Now in this case, this is the, in figure C, this is third mode of vibration. In this case 3 loops are formed. In 3 loops there are 4 nodes, 1, 2, 3, 4. 4 nodes are formed and 3 antinodes are formed. This is the third mode of vibration of the string. 3 loops are formed. Now here we consider the length of string, length of one loop or length of one loop. Vibrating length is equal to where N2 and lambda 2 are the frequency and wavelength here. Vibrating length is equal to lambda 2 by 2 plus lambda 2 by 2 plus lambda 2 by 2. Here see, distance between successive node is, for first loop it is lambda by 2, for second loop it is lambda by 2, for third loop it is lambda by 2. Therefore vibrating length is equal to, it is lambda 2 by 2 plus lambda 2 by 2 plus lambda 2 by 2. Here we can write, it is 3 lambda 2 by 2, it is L. Therefore we can write lambda 2 is equal to, it is 2 by 3 L. Now we know the relation V is equal to N2 lambda 2. Then N2 is equal to, we can write V upon lambda 2. Substitute the value, we get N2 is equal to, substitute the value of V, that is 1 upon lambda 2 under root V, that is under root T upon M. Substitute lambda 2, that is equal to, N2 is equal to 1 upon lambda 2, it is 2 L by 3 under root T upon M. Rearrange the equation, we get N2 is equal to 3 by twice L under root T upon M. Now in this case, suppose we consider this equation, it is for 1 by 2L under root T upon M. It is nothing but fundamental frequency, and we can write it is 3M. This is the third mode of vibration. We can say that it is the frequency of third harmonic. Frequency of third harmonic. It is also called as frequency of second overtone. Thus, we can say that vibration in the string consists of the frequency N to N from equation 1 to equation 2 and from equation 3. We consider the frequencies. The frequencies are N, 2N, 3N, next mode having frequency 4N. Thus, vibration in the string consists of all frequencies. Thus, the vibration of string consists of all harmonics. Thus we can say that N is the frequency, it is called as fundamental frequency. This is frequency for second mode, this is the frequency for third mode, and so on. This is called as fundamental frequency, that is first harmonic. This is called as second harmonic, this is third harmonic, fourth harmonic, etc. What is harmonics here? The integral multiple of the fundamental frequency, it is called as harmonic. Now this is 2N, it is called as frequency of first overtone. This is the frequency of second overtone, and etc. This is thus we can say that the vibration of the string consists of all hormones. Therefore, all hormones are present in a vibrating string. Thank you.